I had done this recording before, but I had put a very simple narrative of whether CO2 absorption of long wave radiation escaping to space is saturated. This argument has been made, misleading argument has been made, that adding more CO2 to the atmosphere is not going to create more warming or any more warming, because all the energy that can be absorbed by CO2 has already been absorbed, and adding more CO2 is not going to cause more of the energy escaping to space in the long wave or thermal radiation is going to be absorbed by CO2, hence the warming will not increase. I decided to do this again because there were many questions and some students or subscribers asked me to provide more details, so I deleted the old video, which was just a narrative. I didn't show any slides, so I went back and collected some material that I hope will explain this better. Where do we want to start? Well, the history is that Svante Arrhenius published a paper in 1896 saying increasing CO2 was already a concern, and that as industrial revolution continues and we burn more and more coal at that time and wood and so on, we would have increasing CO2, which would be increasing the warming. And it was very insightful paper, way ahead of its time. There were related papers before by Eunice Foote and I think Tyndall as well, but nonetheless Arrhenius's paper got some pushback because in 1900 Knut Angstrom did an experiment with a tube which he filled with some amount of CO2 and sent long wave radiation on one end and measured what came out at the other end, and then he changed the amount of CO2, and the length of the tube was fixed when he changed the amount of CO2 and tried the measurements again. And his conclusion from the paper was that increased CO2 didn't change the amount of energy coming at the other end by much. Well, this led to people saying maybe Svante Arrhenius's conclusion about CO2 being a matter of concern by trapping outgoing long wave radiation was not very accurate, and then for a long time this debate went on. And the discussion now is about what is it that Angstrom didn't understand. So we will look at that. So let's start, and then there have been other experiments by the Air Force and so on, which redid the experiments, looked at the absorption at the top of the atmosphere and showed that actually it does matter that when you increase CO2, the amount of energy going out does decrease, which is what means we are trapping more energy and warming the surface and the atmosphere, and the consequences that follow in terms of increasing humidity, glacier melt, sea level rise, extreme rainfall, everything we are talking about in terms of climate change impacts. What are the basic facts that we have to start with so that we don't make the mistake that Angstrom did? This is a nice figure from this paper from Harvard, or at least it was posted on their site. The article came out in a journal called Weather. It's basically showing the radiative flux in watts per meter squared per centimeter of length, and it's looking at wavelengths and wave numbers. Wave numbers, the linear scale shows better the area. This is a log scale, so you have to be careful in micrometers. But nonetheless, the black curve is a model generated spectrum of the infrared radiative flux emitted to space at the top of the atmosphere. So that's what we call OLR. So we're looking at energy coming in from the sun reflected by albedo, what remains, and then what is going out as OLR, so that we understand the energy balance and see how increasing greenhouse gases, land use, etc. are changing the energy balance. And that of course is important for understanding global warming, right, and the climate sensitivity. Colored lines represent the blackbody spectrum at different temperatures. So you can see here regions of reduction in OLR due to H2O rotation bands, CO2 band, so 15 micrometer band. It's called CO2 15 micrometer band because CO2 has many other bands, as we will see in a minute. So that goes from 550 to 800 over centimeter, and O3 is 9.6 micrometer band, and H2O also has multiple bands, but nonetheless we know from Planck's radiation law that as temperatures increase, the amount of thermal radiation increases sigma T to the fourth blackbody radiation. This is not the sun. This is energy that is absorbed and reflected just like our body does. So as you cool the temperatures, the amount of radiative flux drops. There are many details. When you think about the real atmosphere, as we'll see in a minute, atmosphere has a column, and you have pressure decreasing, density decreasing, composition of the air changing, number of molecules decreasing. So energy is coming in, doing its thing, and the system is trying to emit long wave radiation back to space. So how that escape to space happens depends on how tall the column is and what's in it, and the pressure as well, because at higher pressure near the sea level, CO2 does absorb more, but as you go up in the atmosphere and pressure drops, the CO2 absorption capacity goes down, but the energy is purely being absorbed and emitted, because at higher pressures you have a lot of molecules and you can transfer some of the absorbed energy into vibration and kinetic energy and so on, and not just thermal radiation balance, right? So all those things matter, but main thing is that the energy going out is in many wavelengths and many wave numbers, as we can imagine, and there is the atmospheric window, which means in this band there is radiative flux is low, so that means the that's the outgoing long wave radiation is low. So the this matters in terms of the details. When you put up satellites and you want to see the surface, you want to find an atmospheric window where radiation from the surface can be directly seen by the satellite, and so on and so forth. So I won't go into those details. The other thing that really matters that Angstrom missed, and many other people who argue about CO2 saturation also miss, is indeed related to where the energy emission happens. In Angstrom's simple experiment, he was just changing the amount of CO2 without changing the length of the tube and looking at the energy going in and coming out, and said not much changed when he increased CO2. First of all, he didn't increase CO2 by much. Secondly, the change is rather small. If you remember the numbers, incoming solar radiation is around 340 watts per meter squared. Outgoing has to balance that. The changes you are making by increasing greenhouse gases are in the order of 1 or 2 watts per meter squared in the range of CO2 we have changed. So it is a small amount. So the question is, what happens with that change in terms of internal feedbacks of evaporation, increasing water vapor, trapping more energy, and then where is the energy being emitted? If we are trapping more energy because of increased CO2 and water vapor and other greenhouse gases, that means we are sending out less to the atmosphere, which means, if you remember your atmospheric structure, we are warm near the surface, which is the most basic contribution of the greenhouse effect. Because we have a greenhouse atmosphere, energy is being sent back in and energy is being trapped instead of letting it go to space, and that energy is warming the surface. So the surface is warmer than it would be if we didn't have a greenhouse effect. Right? That's the most basic part. But as we go up in the atmosphere, temperature decreases up to the tropopause, increases in the stratosphere because of absorption of UV and ozone formation, and then you have various gradient changes. But notice that the atmospheric surface temperature is still higher than pretty much way up here in the thermosphere, where the gases are very, very low in density. How much energy escapes and how much actually gets trapped determines what the effective temperature is. So in the range that we are in, Where we are emitting the energy is mostly, let's say, in the lower atmosphere, and the energy is trying to escape to space. And as it tries to escape to space, it's not that it's being emitted from one layer. So the kind of calculations Angstrom was making basically assumed that there is a certain length of the air column, which is represented by scaling the tube, which he didn't change with changing amount of CO2. But in the real world, the energy escaping is less, which means we are now emitting from a lower temperature. So sigma T to the fourth is lower, and T to be lower, you have to emit from a higher altitude, which means the length of the atmospheric column is effectively changing. And that's shown by this nice article from the Skeptical Science by an Australian guy who likes the southern hemisphere. So he's saying that the altitude of heat loss when greenhouse effect at pre-industrial level is at a lower level because the temperatures surface temperatures are lower than now, no greenhouse warming, no anthropogenic warming. Then the energy escaping is essentially balancing the energy absorbed. So you are emitting from some altitude, but as we trap more and more energy with greenhouse gas increases, the radiative imbalance due to enhanced greenhouse effect is causing less energy to go out, which means you are emitting from a lower temperature. Colder temp. I have to be careful where I point. We are still emitting from somewhere here. So we are basically increasing the altitude at which the energy is being emitted, right? So this is very critical to remember. So the atmospheric column in some sense is expanding if you want to think of a tube experiment. It depends on details, as we'll see in a minute, in terms of the spectral band of the energy that's going out, as you can see here, and where it's being emitted. So these are critical things that were missed by Angstrom. So very nice long articles by Ray Pierre Humbert, who used to be at Chicago and I think is retired now. Incredibly good scientist, climate scientist, who has written a book on climate science as well, which is much more focused on the fundamentals and planetary atmospheres and so on. A bit hard to read because it's very detailed in mathematics and physics, but he writes very nice articles here. Basically, this is from Spencer Weird with Ray Pierre Humbert. We'll see next one by Ray Pierre Humbert as well. It calls this argument about CO2 saturation as a saturated gassy argument, and the point is they make is very simple. If you take the absorption factor of the wavelength based, so we are in the long wave radiation, that you have to remember, then there are many bands, wavelengths at which the energy at these wavelengths are absorbed. So there is no single band. So we just looked at the maximum, so the CO2 band in this range, but CO2 has many other absorption bands, and this figure basically shows that if we were at 1 CO2 in the pre-industrial period, let's say at 280 ppm, we would be saturated in this band here, okay, which is actually even if it's saturated at lower level because we have increased CO2 enough, it doesn't matter, because as you increase CO2 you keep shifting the absorption factor and absorb more wavelengths, because there are many wavelengths that are still not even close to being saturated. So even if you saturate certain bands at 1 CO2, let's say at a lower atmosphere with higher pressure, where the emission is happening in the upper atmosphere is still not even close to being saturated. And that's shown here, that in fact if we did manage to quadruple the CO2 from, let's say, the pre-industrial level, we will just be expanding the absorption levels, or we'll be, let's say, lowering the absorption level a little bit, but we will still not be saturated because we will just expand the number of wavelengths which can continue to be absorbed by the CO2. And we are not even remotely close to quadrupling the CO2, because we started with 280, we are now at 520 420 something, sorry. 520 would be very high. So even if we quadruple to 1,000, more than 1,000, we will still not be saturating. That's the main point you have to remember, that there are many bands, because this line is got many peaks and valleys, and it's the valleys that matter when photons of energy in the thermal band are trying to escape to space and are being absorbed by CO2, because CO2 has it's a symmetric molecule, so not a natural greenhouse gas if you think about N2 and O2 sense, but because it has a bending mode, it does absorb the photons of long wave energy. And of course there are others as well. So in the second part, Rapier, Humbert and Spence Weird go into more details about why the experiment made by Angstrom and then by this guy Hercock were not exact. Okay, so if you think about energy escaping from the surface to space along the way as well from the atmosphere at various levels, the column of atmosphere has high air density and pressure and keeps decreasing as we go up, and temperature keeps decreasing, pressure keeps decreasing. So the energy escaping begins to drop exponentially. So if you think about transmission in 10 to 22 micron band and length of the tube in meters, you will drop exponentially. So Angstrom was somewhere here in the 30, well, he was in the 30 centimeter range, I think. Nonetheless, equivalent tube length for one CO2 is somewhere here. If you think about the tube experiment as opposed to the atmospheric column, if you increase the equivalent tube length, considering this transmission dropping exponentially, to do the experiment correctly, you will have to increase the tube length, which they didn't do, which means they missed this exponential decay part. Hence, the measured difference in the long wave energy coming out at the other end with changed CO2 concentration was underestimated. That's why they concluded things wrongly, that Arrhenius's work was not to be worried about. And if you increase to 4 CO2, you will again drop here in terms of the or you will increase the effective tube length, which is basically saying what we said here, that the height of the atmosphere increases considering where the energy will go out to space. Okay, I hope that's clear, because these arguments are important and yes, the radiative calculations are kind of complicated. Looking at another way is to also see how Hercock actually produced the outgoing long wave radiation he used. He used energy coming from 100 degrees C black body, which is like boiling temperature of water. So transmission relative to the 100 degrees C black body is actually different. He was in this range in meters compared to what sun's energy or Earth's outgoing long wave energy is in. That's the realistic situation, and this is what he did. So the experiments were not ideal and the conclusions were rather misleading. The main message I would leave you with is that in fact we are not even remotely close to saturating the CO2 band. So each additional molecule of CO2 or additional ton of CO2 we add is going to keep absorbing more long wave radiation. So we will cause more and more global warming for a very long time if we keep adding more CO2. Okay, I hope this is clearer than the previous narrative I had, and I'll post this again on the same in the same chapter of the Introduction to Climate Science, and then I'll post again on social media to make sure that this also gets looked at. Thank you for all those who asked the questions, and if this doesn't clarify things, let me know. I'll see if I can add more. Okay, see you in the next podcast.